This is SpaceTime Series 27, Episode 115, for broadcast on the 23rd of September 2024. Coming up on SpaceTime, how black holes eat stars, new revelations about the Earth's mantle, and it seems water is far more widespread on the Moon than previously thought. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have developed a new computer simulation detailing how monstrous black holes at the centres of galaxies can physically rip apart and consume an entire star. The new research, reported in the Astrophysical Journal Letters, captures this complex process in great detail, also providing new insights into the mysterious optical and ultraviolet emissions observed during these catastrophic events. The study's lead author, Daniel Price from Monash University, says the program represents the first self-consistent simulation of a star being tidally disrupted by a supermassive black hole, followed by the evolution of the resulting debris over the course of a year. When a star passes too close to a supermassive black hole, the intense gravitational forces of the black hole tear the star apart in a process called a tidal disruption event. The debris from the unfortunate star then forms a stream of material which will eventually feed into the black hole. But this material doesn't disappear down the black hole all at once. First, it creates a swirling accretion disk around the black hole. And as the material goes around in this accretion disk, it's crushed together through intense friction, while at the same time being ripped apart at the subatomic level, in the process releasing vast amounts of energy across the electromagnetic spectrum, but mostly in X-rays. Eventually, the superheated debris passes a point at the inner edge of the accretion disk called the event horizon. This is the point of no return. The distance from the black hole, where the gravitational pull of the black hole becomes so strong, escape velocity exceeds the speed of light. And since nothing can travel faster than the speed of light, the material is doomed to fall forever into the black hole singularity, a place where the laws of physics as science understands them breaks down. But not all the ill-fated material is destined to disappear into the black hole. See, black holes are messy feeders, and so some of this material is captured by powerful magnetic fields before reaching the event horizon. So instead, this material is fired out into space perpendicular to the accretion disk at close to the speed of light. Price says the simulation provides a new perspective on the final moments of stars in the vicinity of supermassive black holes. By capturing the full evolution of the debris, astronomers can try and connect the simulations with the growing number of observed star-shredding events identified through telescopic surveys. Price says the study provides new avenues of research into the behaviour of matter in the most extreme gravitational fields in the known universe. It also displays fascinating details about the life cycle of stars and black holes. However, many aspects of tidal disruption events remain poorly understood. For example, the new simulations show that this debris forms an asymmetric bubble around the black hole, reprocessing the energy and producing the observed light curves with lower temperatures, fainter luminosities, and gas velocities of 10,000 to 20,000 kilometers per second. Other mysteries explained by the new simulations include why tidal disruption events are observed at optical rather than X-ray wavelengths, where X-rays would be expected from the accretion onto the supermassive black hole. Also, why temperatures observed are consistent with the photosphere of the star rather than the expected hot accretion disk itself. Why observed star-shredding events are fainter than expected from models of black holes efficiently consuming material. And why the spectra of the observed events finds material expanding towards us at a few percent of the speed of light.
Well, it's amazing, actually, we can even detect these things. So tidal disruption is just the name for what happens when a star wanders too close to the black hole in the middle of a galaxy, so a supermassive black hole, and basically gets spaghettified. So spaghettification, I guess, is the non-technical term for tidal disruption. This sort of thing takes place in the middle of galaxies. So we see this in the middle of other galaxies. We see it as a transient event. The middle of the galaxy goes bright, so stays bright for a year or even several years, and sort of fades again over time. And we think this is due to black holes snacking on stars.
I remember about, would have been a decade ago now, that a large gas cloud was heading towards Sagittarius A star, which is the supermassive black hole at the center of our galaxy. And it was getting really exciting because it looked like this huge gas cloud was about to be gobbled up by the supermassive black hole. And we were watching, and it made a close pass, and it never happened. It just went on its merry way, and that was sort of a bit of a letdown, really. But ever since then, just the idea of tidal disruption events has been a fascinating and perplexing process for me. We don't really get to see them close up and personal very often.
Actually, I remember the G2 incident quite well, because we were lots of people predicted what should happen in that case. What was funny is that everyone got it completely wrong. So there's a good example of actually simulations telling you something which didn't match our observations.
At the time, of course, there was still a lot of debate. Is it a cloud or is it already partially tidal disrupted star?
Indeed.
There was a lot of debate about all that, which made the whole thing even more exciting.
We're actually working on these G objects at the moment. That's my next paper. So it's still actually a fascinating question about what those things are in the middle of our galaxies. There's a number of them now called the G objects. The G2 cloud interesting thing hasn't gone away.
The black hole doesn't eat the star all at once, but it tears strips off it as the star orbits around. Do you ever get a situation where something really large, a supermassive black hole, maybe a billion times the mass of our sun, would that still operate the same way by tearing strips off an orbiting star, or is that something that could gobble a star in one gulp?
That's a really good question. So you're exactly right. So if you start to get to sort of billion solar mass black holes, it's all about where is something we call the event horizon. So the event horizon is where light can't escape from the black hole. In fact, nothing can escape. And so if that event horizon is very large, like it is for a billion solar mass black hole, then you're exactly right. The star would get completely swallowed whole. And actually that would be fairly unexciting in the sense that we would not see anything special happen. Stars in distant galaxies are quite faint compared to the galaxy itself, so we would just see nothing happen. And in fact, we do see evidence for that the tidal disruption events that we observe, they come from sort of million or 10 million or maybe even some from 100 million solar mass black holes. But when we get to a billion solar mass black holes, there's no tidal disruption events. And so we think that's exactly what you just said, which is that the stars just get swallowed whole.
And we've seen that on the stellar scale as well, haven't we? Where, say, two neutron stars merge together, and sometimes there's a huge explosion, gamma ray burst, but other times the process suddenly stops and the whole thing disappears because it's become a stellar mass black hole.
That's a really good analogy as well. So the key thing is about the mass ratio. So it's whether you have two objects of the same mass that are merging together or whether you have objects of very different mass. So in the case of a star and a black hole, so for example, a neutron star merger, the neutron stars would tear each other apart by the tides, and they sort of tear each other apart equally. But that can get very different. If you start to get a neutron star and a black hole, then the black hole can tear the neutron star apart and being relatively unaffected itself. And so if we come back to the stars encountering million solar mass black holes, then what you tend to get is the black hole doesn't care. It's just sitting there. It's so much heavier than the star. But we've had this prediction for a long time back from Martin Rees, the British Astronomer Royal, in 1988. He made a very clean prediction, which is also seen in our simulation, that around this kind of black hole, stars should mostly come a little bit like comets come towards the sun. They tend to come on these, what we call parabolic orbits. So they just, they get a little kick and they just happen to plunge towards the sun. And that's the same with a star, sort of just gets a little kick in a galaxy and just happens to plunge towards the black hole. And what happens is that half the star becomes bound to the black hole and half the star just carries on its way. So if you imagine that happening, what you have is half the star plunging down towards the black hole, half the star being flung away to infinity. So the star gets literally ripped in half and starts to look like a very, very long strand of spaghetti. And so that's the sort of extreme mass ratio. So when you get to the star that's so much smaller than the black hole mass itself, it just gets spaghettified into this big long thing of pasta, and then half that strip of pasta then just starts to feed the black hole. And what comes around again on the second passage, and that's a bit we haven't been able to simulate before, is that what happens next? So that half the star's coming back, does it just get eaten, or does it go around and make an accretion disk, or does it do something else? And well, it's quite interesting what does happen.
Well, don't leave us in suspense.
Well, so the mystery is, again, how you sort of what we call circularize that material. So could you form it into some kind of accretion disk? And the expectation was, yeah, you would swallow a fair bit of material and generate X-rays. But what happens is, like we said, a black hole is one of the best ways to generate energy in the universe. So you only need a little drip feed and you start getting this huge hot power source going in the middle. It's like a volcano going off. So you only start to feed the black hole. So the stream comes around. One of the general relativistic effects is the orbit will precess slightly. So that means the stream actually tends to collide with itself. And that collision causes a little bit of material to plunge towards the central regions. And as soon as you start feeding that thing, it starts powering this outflow. So anything else that comes in just tends to get blown away. Another way of thinking about it, like we said, the black hole's a small object. It's very hard to stuff material down the hole. So most of the material actually just misses. But then you've got this huge heat source in the middle, and that just powers this very strong outflow. And so, in fact, that's what we see in tidal disruption events. One of the ways they're identified is that when you take a spectrum of these things, you find that the material is all being flung towards us at 10 or 20,000 kilometers a second. So that's around 7% of the speed of light. That's extremely fast. And so we actually get those kind of speeds in the simulation. We find this big ball of gas develops. And the key thing about the ball of gas is that it's not see-through. So like we said before, that's what we call the reprocessing layer or the smothering of the black hole. And that's the thing that hides the X-rays and gives you this kind of glowing big ball of material that we call it the Eddington envelope. It's a kind of black hole, solar system-sized star, but it's expanding rather than just staying still.
In your simulations, can you compensate for things like time dilation? How would that affect what's happening?
Yeah, so those effects are all in the simulation, that's right. So relativity messes with your mind if you start to think about it. But, you're absolutely right that those sort of things, so for example, material in the simulation actually never crosses the event horizon. So we actually just cheat a little bit and just delete it if it gets very close. But according to Einstein's theory, you would never actually watch someone crossing the event horizon of the black hole from the outside.
I like to say it falls forever.
Indeed, yeah. So that's, for example, one of the things that just happens naturally in the computer. You do see things would just fall forever. But, of course, in a computer, that tends to give you an infinity and the code crashes. So we try to just skip that bit. But, it is how the physics work.
That's when the computer says, danger, Will Robinson.
That is one of the tricky bits. It is hard to say exactly what something will look like, especially when you get to those regions close to the black hole.
How often do we normally see tidal disruption events?
So in a galaxy like the Milky Way, obviously we can't sit and stare at our black hole for millions of years, but we can see similar other black holes in the nearby universe. So we think, the rate's actually been going, people keep revising it upwards, but the current idea is something like once every 100,000 years. So if you stared at the black hole for 100,000 years in our galaxy, then a star would get gobbled. Now that sounds like a long time, and it certainly is for our Milky Way, so we don't expect one in our lifetime. But yeah, you can imagine if you start looking at 100,000 galaxies, and there's plenty of them in the sky, that you would start to get a lot of these events taking place.
And, of course, there'd be evidence of that, things like, say, the Fermi bubbles.
Indeed, yeah. So that's one of the questions, actually, is we can see that our black hole, while it's a bit of a sleeping giant now, we think it's been definitely active in the past, and we can see, as you said, some evidence for that in the galaxy. Actually, that's one of the questions that people want to know, is because once a black hole starts getting active, that's something we call an active galactic nucleus. It has quite a big effect on the surrounding galaxy. And so knowing, for example, what the duty cycle is, so how often this activity comes and goes, it's a little bit like living next to a volcano. You'd like to know, volcano might be sleeping now, but you'd like to know how often they erupt and how often, if it does erupt, what's going to happen. And so that's something that people want to know when they study galaxies. What's the sort of effect of having a black hole in the middle of your galaxy? It sort of shuts off a lot of formation of stars and things like that. So it has a big effect on its surroundings when it gets active like that, much like a volcano on surrounding villages.
Being a barred spiral galaxy as opposed to a grand design spiral, does that play a different set of circumstances in terms of the frequency of black holes engaging in tidal disruption events? Barred spirals like the Milky Way become barred because they have a buildup of mass near the centre, don't they?
Yeah, so the bar tends to develop from an instability in the pattern of stars orbiting the black hole. And one of the things that we think happens a fair bit in barred spiral galaxies is the more efficient flow of gas towards the central black hole. Actually, there is an association of a particular kind of galaxy galaxy with tidal disruption events. And it's not fully understood why that is, but it tends to be in more sort of elliptical-looking galaxies that you seem to get these things going off. And we don't fully understand that. There's some possible explanations for why that association might be the case, but it's not fully understood. But obviously one of the things that you could do in a spiral galaxy or a grand design spiral is you have maybe a lot more gas in it, and you could feed a bunch of gas to the central black hole. And when that happens, that's more likely to produce something we call a quasar or an active galactic nucleus, rather than, so a tidal disruption event is really a sort of discrete snack on a star rather than a sort of continuous feeding of the central region.
I guess if you got a quasar or something like that, you're blowing material away too from the black hole, and that material could be stars. Whereas when you're old, red and dead, meaning an elliptical galaxy, then you haven't got that much gas there anymore. So
That's right.
And the stars are all orbiting any which way, including loose, so anything's possible.
Actually, one of the big questions in the field as well is actually how you get very massive black holes in the universe. So we don't fully understand how black holes grow. And one of the mysteries from recent James Webb observations is we're starting to see these sort of billion solar mass, 10 billion solar mass black holes in the very early universe. So in, the first maybe 100 million years of the universe, which is really when the universe is a young adolescent.
That's got to be just from collapsing gas, doesn't it? I mean, you couldn't merge that many stellar mass or intermediate mass black holes together that quickly, one would think.
Oh, so that has been the thinking, but it's still, it's unclear if that's true. So there's a big question about what were the seeds of the earliest of black holes. And there's some evidence that you could maybe do that with star clusters that are maybe 10,000. So you could maybe 10,000 solar mass black holes with just merging stars together. And once you've got a 10,000 solar mass black hole, it's not so difficult to get a 100,000 solar mass black hole by feeding stars to it. So it's an open question, so it's definitely not solved. But it's not so crazy that you could actually grow black holes by just tidally disrupting stars and then merging black holes together. It's definitely not the preferred idea, but it's not completely nuts to suggest that.
Well, of course, the universe was a much closer together thing back then, so stars were a lot closer anyway, so they were closer to their black holes.
Well, that's one of the things. So we think, for example, remnants of things like the globular clusters in our own galaxy. So if you look up at the night sky, you'll see Omega Centauri. We think those are little intense bursts of star formation that took place in the early part of the universe. So those kind of, really dense star clusters, they could probably much more easily make black holes. And, well, one of the challenges in globular clusters has been to look for these intermediate mass black holes with, some evidence that they seem to be there.
They just found an Omega Centauri, didn't they?
Yeah, I think it was certainly claims that there are intermediate mass black holes in these nearby globular clusters.
Well, there was something like 150 of them orbiting our galaxy, so there's plenty to choose from.
So the thing about the globular clusters is they're really old, so that they're what we call low metallicity stars, so that's stars without lots of hydrogen and helium and not many of the heavier elements. And those, we think, come from the very early universe. So, for example, dating some of those globular clusters, we think some of them are maybe up to 12 billion years old. In fact, there was an old problem that they were actually older than the universe itself, which was a bit of an issue. But people fixed that with better distance estimates, and it seemed to all match up again. But, they are sort of remnants from that early stage of the universe where we think probably things are a bit more violent and a bit more, it's a bit easier to form these very dense star clusters, for example.
That's Professor Daniel Price from Monash University. And this is SpaceTime. Still to come, new revelations about the composition of the Earth's mantle and the discovery that water is actually fairly widespread across the surface of the Moon. You just got to know where to look. All that and more still to come on SpaceTime. Well, it looks like it's time to rewrite the geological textbooks of the planet. A new study has found that the chemical composition of the Earth's mantle is basically the same everywhere and only changes into unique compositions as it passes through different layers of crust closer to the planet's surface. The new findings, reported in the journal Nature Geoscience, are based on an evaluation of volcanic hotspots around the globe. It shows that lavas from hotspots, whether erupting in Hawaii, Samoa or Iceland, likely all originate from what appears to be a worldwide uniform reservoir in the Earth's mantle. It means the Earth's mantle is far more chemically homogeneous than scientists previously thought. One of the study's authors, Matthias Schmidt from the University of British Columbia, says the discovery quite literally turned science's view of hotspot lavas in the mantle upside down. He says, in a way, the Earth's lavas are much like the human race, a beautifully diverse population with a common ancestor, but which developed differently wherever it went. Of course, research into Earth's mantle has always been complicated by the simple fact that it can't be sampled directly. So instead, researchers need to engage in a bit of geoscientific detective work. They study this important part of the planet through trace element isotopic analysis of the lavas that come from the mantle and which is erupted at oceanic volcanoes around the world. The vast differences in composition in these lavas, along with the assumption that the isotopic composition of magma doesn't change between its source and the surface, has wrongly led to a general view that mantles contain distinct reservoirs of different ages, located in different regions, and formed by different processes. The observations made by Schmidt and colleagues, however, indicate the reality could be quite different. Schmidt says by looking at a specific set of elements, scientists were able to discern chemical effects of various processes that act on magma melts on their way to the surface. And this allowed them to discover that all hotspot lavas actually share the same starting composition. That means the lavas only come out differently on the surface because the magmas are interacting with different geology as they ascend up through the crust. The Earth's mantle is a seething layer of molten and semi-molten material comprising about 84% of the planet's volume, lying between the Earth's liquid iron outer core and its thin surface crust. When magma derived from the mantle penetrates the crust and erupts onto the surface, it's called lava. Knowing what the mantle is made of is central to science's understanding of how the planet formed and how the mantle itself developed and evolved over time. It may also provide clues as to why the mantle behaves the way it does, how it drives plate tectonics, and what its role is in the global cycle of elements. Despite shedding entirely new light on hotspot lavas in oceanic parts of the world, the analysis also reveals an exciting new link to basaltic lavas on the continents. These melts, which contain diamond-bearing kimberlites, are fundamentally different from magmas found at oceanic hotspots, but they nevertheless still have the same magma ancestor. This discovery really is a game-changer when it comes to models of Earth's chemical evolution and how science looks at global elemental cycles. Not only is the mantle much more homogeneous than previously thought, it likely also no longer contains primordial reservoirs. These were entities that were once thought to exist and were needed to explain the data scientists were seeing. Trouble is, the hypothesis of these things could never really be reconciled with the very concept of mantle convection. And so now, thanks to this new study, we can dismiss it completely. This is SpaceTime. Still to come, scientists discover there are far more widespread water resources on the Moon than previously thought. You've just got to know where to look. And later in the science report, a new study finally pins down where the Australian wild dog the dingo really originated from. All that and more still to come on SpaceTime. A new analysis of maps from both the near and far sides of the Moon are showing scientists that the lunar surface contains vast amounts of water. Trouble is, it's mostly locked in the lunar regolith. The findings, reported in the Planetary Science Journal, suggest that there are multiple sources of water and hydroxyl in sunlit rocks and soils, including water-rich rocks excavated by meteor impacts at all lunar latitudes. By the way, hydroxyls are functional chemical groups of molecules comprising a single hydrogen and a single oxygen atom, but missing the second hydrogen atom needed to turn it into a water molecule. See, the solar wind carries normal hydrogen atoms to the Moon, where the molecules interact with oxygen already on the surface to form both hydroxyls and water. The study's lead author, Roger Clark from the Planetary Science Institute, says future astronauts should be able to find water even near the equator simply by exploiting these water-rich areas. Previously it was thought that only lunar polar regions, and in particular the deeply shadowed craters at the poles, where sunlight never reaches the crater floor, were likely to contain abundant water supplies frozen as ice. Clark says knowing where the water is located not only helps scientists better understand lunar geologic history, but also where astronauts may find water in the future. That water could then be used for drinking, or split up to be turned into rocket fuel, or simply for breathing. Clark and colleagues based their findings on data from the Moon Mineralogy Mapper Imaging Spectrometer aboard the Indian Chandrayaan-1 spacecraft, which orbited the Moon during 2008 and 2009, mapping water and hydroxyl on both the near and far sides of the Moon in far greater detail than had ever been done before. The mapper used infrared spectroscopy to search for the fingerprints of both water and hydroxyl in the spectra of reflected sunlight on the lunar surface. While a digital camera records 3 colours in the visible part of the electromagnetic spectrum, the mapper instrument recorded 85 colours in the visible spectrum and also well into the infrared. Just like we see different colours from different materials, the infrared spectrometer can see many infrared colours to better determine the composition, and that includes water and hydroxyl. The water may be directly harvested by heating rocks and soils. The water can also be formed by chemical reactions, liberating hydroxyl and combining 4 hydroxyls to create oxygen and water. By studying the location and geologic context, the authors were able to show that water in the lunar surface is metastable, meaning H2O is slowly destroyed over millions of years, but with hydroxyl, the OH, remaining. Also, a cratering event that exposes subsurface water-rich rocks to the solar wind will also degrade with time, destroying H2O and creating a diffuse aura of hydroxyl, OH. But the destruction is slow, taking thousands to millions of years. Elsewhere on the lunar surface, there appears to be a patina of hydroxyl, probably created by solar wind protons impacting the lunar surface, destroying silicate minerals where the protons combine with oxygen in the silicates in order to create hydroxyls, in a process called space weathering. Putting all the evidence together, Clark and colleagues see a lunar surface with complex geology, with significant water in the subsurface and a surface layer of hydroxyl. Both cratering and volcanic activity can bring water-rich materials to the surface, and both are observed in the lunar data. Our Moon is made up primarily of 2 kinds of rocks. There's the dark mare we see from the Earth, which gives us the man in the moon image. This is basically basaltic rock, like solidified lava. Then there's the andesitic rocks, which are lighter and found in the lunar highlands. It's the andesites which contain lots of water, while the basalts contain very little. The study also sheds new light on previously known mysteries. When the sunlight is shining on the lunar surface at different times of the day, the strength of water and hydroxyl absorptions change. That led to the calculation that a lot of the water and hydroxyl had to be moving around the Moon on a daily cycle. However, this new study showed that very stable mineral absorptions of water and hydroxyl show the same daily effect. But on minerals like pyroxene, a common igneous silicate material on the lunar surface, they don't evaporate at lunar temperatures. The reason for this effect is instead due to a thin layer of enriched composition and/or soil particle size that's different from deeper down in the soil. So when the sun is low in the lunar sky, light transmits through more of this top layer, strengthening the infrared absorptions compared to when the sun is higher in the sky. Now don't get me wrong, there may still be water moving around, but to know how much, new studies will be needed to quantify the layering effects. Also, if you recall, the lunar rover tracks appear to be darker in images from the Apollo-era rovers. That's another indicator that the surface layer is thin and very different. Related to this thin surface layer are the expressions of enigmatic features on the Moon called lunar swirls. These are diffuse patterns in visible light in several areas on the Moon. Now, it's magnetic fields which are thought to play a role in swirl formation by diverting solar wind, which would also reduce hydroxyl production. And that matches up with earlier studies which show that lunar swirls are deficient in hydroxyl. The new study confirms this but also shows more complexity. That is, the swirls are also low in water content, but are sometimes higher in pyroxene content. This new study, using lunar global hydroxyl maps, also shows never-before-seen areas that are similar to known swirls, but have no diffuse patterns seen in visible light, thus can only be seen in hydroxyl absorption. These new features may in fact be old eroded swirls, and include new types, including arcs and linear features. By mapping the Moon in new ways like this, the lunar surface is showing scientists that it's far more complex than previously thought. Good to know as we move closer to the Artemis 3 mission in 2026 and man's return to the lunar surface. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. New climate models are warning that future droughts could be even worse than previously thought. A report in the journal Nature claims scientists calibrated models with historical observations of the longest annual dry spells, that is, the longest number of consecutive dry days each year, between 1998 and 2018. They found the average longest period of drought could end up being 10 days longer by the end of the century than previously predicted. The authors say the findings emphasise the need for a reassessment of drought risks around the world, and they highlight the importance of correcting existing biases in climate models to increase confidence in their projections. A new study claims just taking 3 minutes of exercise every half hour in the evenings could help you sleep. The findings, reported in the British Medical Journal, are based on a small study investigating how exercise late in the day could impact on sleep. The authors recruited 28 people to wear trackers and then monitored their activity and sleep. On 2 days, about a week apart, they were each asked to spend 4 hours in the lab from around 5 p.m. in the afternoon. In one of these sessions, the participants sat for an entire 4 hours, while in the other, they completed an equipment-free 3-minute resistance exercise program every half hour. The authors found that the participants slept for an average of 27 minutes longer after they did the exercise program session compared to the simply sitting around session, with no differences in sleep quality. New archaeological research has discovered clear links between fossils of the iconic Australian native dog the dingo and dogs from East Asia and Papua New Guinea. The findings, published in the journal Scientific Reports, suggest that the dingo must have come from East Asia via Melanesia, and it challenges previous hypotheses that the dogs arrived from India or Thailand. Previous studies had used traditional morphometric analysis. This looks at the size and shape of the animal using calipers in order to trace the dingo's ancestry to South Asia. However, the new study used more sophisticated 3D scanning techniques combined with geometric morphometrics on ancient dingo specimens to clearly show that they're really most similar to Japanese dogs, as well as the singing dogs of Papua New Guinea and the Highland wild dogs of Irian Jaya. The authors also found that modern-day dingoes have evolved to become larger and leaner, standing an average of 54 centimetres tall compared to between 40 and 47 centimetres for their ancient ancestors, a size which is also much closer to their contemporary relatives in Southeast Asia and Melanesia. Well, it seems the latest fad in Japan and the United States for the paranormally inclined is what they're calling a ghost-detecting stone. It's claimed that this stone changes colour when ghosts, angels or evil spirits are lurking about. Now, of course, the first problem is we're assuming that ghosts, angels and evil spirits are real. You've also got the problem that it's not really a stone, it's just a chunk of plastic with some electronics and a battery inside. And at $100 in Aussie dollars, it ain't cheap. So, does it work? Well, I guess it depends on whether or not you want to believe, as Tim Mendham from Australian Skeptics explains.
It's weird. It's little stones about the size of a couple of centimetres across, round about that size, that supposedly change colour when they're surrounded by some sort of paranormal activity. They sell for about $60-odd US, which in Australian money is about $100. So they're not cheap, but they supposedly change colour when they glow. They glow green during unusual paranormal activity. They glow blue when there's an angelic presence, and they glow red when a ghost is nearby. So I'm not quite sure what the paranormal activity is compared to a ghost or an angel. But anyway, they go through these three colours, and basically it's a search mode which is activated manually. It's hard to tell by the pictures. I don't own one, I should add, and no one apart from the manufacturer is exactly sure how they work. Probably if you try to take them apart, they are plastic stones.
So they're not real stones.
They're not real stones. No, they have a sensor, so they obviously have a chip inside of some sort, and they sort of do various things. So there's a search mode which scans around. There's an automatic mode which automatically scans the environments every 10 minutes, and there's a barrier mode which is designed to block dangerous spirits from harming the user. Now, I don't think they're exactly the same as what we used to call mood rings, which were the liquid crystal things that you heated up and they changed, because of the change of temperature, they change colour, supposed to indicate your passion level. It's a Japanese thing. It's called Bakatan Reiseki, which means a stone that searches for ghosts. Not particularly the most exciting name, but yeah. And it has a crystal ball perhaps inside it, and it's made of ABS thermoplastic, so it's not a real stone.
What does it tell you about the sort of people who buy this sort of thing? I mean, a lot of people will buy it for the novelty value, sure, but there are going to be a lot of people out there who are going to buy it because they're serious. They think it's going to help them.
There will be. There's a lot of people who use a lot of gadgets, pick up radio signals, that sort of thing, ghostly signals, etc., on their particular handheld device, or it's an app on a mobile phone, something like that. So this is supposed to be something that will give you an indication if there's something there. So do these apps and little portable devices do the same thing. I don't think you can record the events. It's just an indicator, whereas a handheld device or an app might record signals, radio signals, electronic voice signals, that sort of thing, electronic voice patterns, that sort of stuff. So is it a substitute? No. Now, this is assuming it works, and I'm not going to assume that by a long way. You have to have more than a passing interest. You'll use it once or twice, and then it'll go in the drawer, probably, and it's left there forever, and you pull it out after a while and say, what's this? But there are alternatives. I don't think serious ghost hunters would use it very much. It's for the people having fun. People doing a Ouija board seance in the middle of the night, having fun and a few drinks, might put it down to see.
Well, then you'll find some spirits.
Problem. You will.
That's Tim Mendham from Australian Skeptics. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.